in here is like, it's like noise and not her.
Upper and lower bounds for the linear model in high dimensions. So here's the linear model. So here's the linear model. You're probably familiar with that one. So y is a response vector. Its dimensions are n times 1 squared, but x is an n times p matrix. The unknown parameter is the vector of regression coefficients. Okay. So the number of parameters is p, and it's going to be large. So you have to do something to deal with the high dimensionality of the problem. Okay, then the lasso is like this. So you take the minimizer of the following. You take the sum of squares. I normalized by n, that's my habit. You don't have to. Okay, and then there's a penalty which is proportional to the L1 norm of the coefficients. And I put a 2 here because otherwise I have to write 2's at other places. Okay, so I guess this procedure is known, and maybe you worked on the theory or applied it. Okay, so now I want to show, so I talked about effective sparsity on Friday, but maybe you were not there. But anyway, I want to go a little bit into that topic. So you need a certain condition to get good theoretical properties of this estimator. And that condition, I call it compatibility, but it's related to restricted eigenvalues. And I want to really to show you that this condition is really quite natural, so that's why I'm going to derive it here. And really, to make life simple, let's forget about the noise for a moment. Okay? So I'm going to cancel the noise. Just for the development of the theory. And later on I'll show you that it's quite useful to think about that case too. So if you have no noise, I have this kind of thing. So there's no noise, so y is just x beta 0. So then you get x b minus beta 0 squared b1. Okay, so let's consider this problem first. There's no noise now. Okay, now I'm going to write down the derivative and put it to 0. And that's called the KKT conditions. Well, Karush-Kuhn-Tucker conditions. That is taking the derivative of this term. That's x transpose x beta minus beta 0. And then a 2, but there's a 2 on the other side too, so I'm just cancelling the 2. That's the derivative of this term. And then the derivative of this term is the subdifferential, call it z. So you put the derivative to 0 and solve. Maybe I should put a star here, maybe that's better. So this is the subdifferential of the absolute value function, or of the L1 norm. So this says that Z is a vector which components are the sign of beta star. And if beta star is 0, I don't care what z is, but it's something between -1 and 1. Okay? So z, the largest value, it's a sign, so that's an absolute value less than 1. Okay. Okay, now I'm going to multiply by beta star minus beta. So what I get then, if I multiply here by beta star minus beta transpose, you get again this quantity x beta star minus beta 0 squared. And then I multiply by beta star minus beta on this side too. So this is lambda beta star minus beta 0. So far so good. Okay, so now we have, let me just write it. So it's beta, the true beta transpose z star minus, and a lambda here, and then the beta star transpose z star. Okay? Okay, now I'm going to use that the sup norm of z star is less than 1, so I can bound this term by the L1 norm of beta 0. Okay? And this term is exactly the L1 norm of beta star. Okay? Now we're almost done, and then we get a result. So let's see. Let me call S0 the active set of beta 0. So that's the set where the coefficients are non-zero. You can be more precise here, but let's not do that. We just look at strong sparsity. S0 is going to be the cardinality of that set, so the sparsity. And I'm going to write beta, or maybe B, maybe better. BS0 is going to be BJ J in S0 and B minus S0. So I'm just going to split up a vector according to being in the active set or not. And let's see, then we can write here, and so this is the same, right? And here I can split it up, so you get okay, minus lambda okay, I just split it up in the inside and outside the active set. And here I use the triangle inequality. We're almost done. Okay, lambda beta S0 minus beta S0 star. So, and now comes the trick. Let me put it here. Here. I'm going to define the following quantity. I put a hat here, don't worry about that. Squared minimum x b squared such that beta S0 is equal to 1. And I normalize, so times S0, so like this. So this is the crucial quantity. This is called the compatibility constant. So it's just introduced to make the following step. Okay, so if this is negative, I'm done. Then I just proved that the prediction error for the lasso is less than or equal to 0, and then I'm done. So it's 0. So I can. That's not an interesting case. So, but if this is positive, it means that this term is larger than that term. And then with this normalization, you can bound it by lambda. And then because of there are no squares here, so there's no square. Let's put a square. So there's okay, I'm putting the square here. Kappa. Oh, sorry, the kappa is downstairs. And this is just kappa S0. I put a hat here because of the fixed design. So that's that one times x beta 0. Oh, no square here. So now it's without the square. So here. Yeah? So if you are okay just defining this funny quantity, you get a bound for the prediction error of the lasso. So this term then cancels with that term, and then you get x beta star minus beta 0 less than, oh well, let's put the square, then you get, I don't like square root n here, so let's put the square here. Yeah, so you just put it to the other side, you get lambda squared S0 divided by kappa squared S0. Yeah, so that's a bound for the prediction error. And I want to show you now, I'm going now to the slides, that it's also so it's an upper bound and it's also the lower bound. Okay, let's see.
Mister, what's the point of this k hat introducing? I didn't understand.
Okay, that's just to make that last step. So this k hat is just depending on on the design. It's some property of the design, and it occurs here. I'll explain it a little bit further. So that's the main thing. This is a compatibility constant. That's the point. Compatibility constant. So the idea is, if you look in the literature, similar quantities appear, but they are called restricted eigenvalues. This one is a little bit different, a little bit less stringent, which allows me also to get the lower bounds, because actually what appears in this upper bound also appears in the lower bound. So apparently that's the main quantity that rules the whole thing. So let me try to give the details now in the slide. So yeah, sometimes it gets a bit technical, and then well, maybe all the time. So then you just zoom out, okay? Yes?
I don't get the last inequality.
This one?
The last inequality on the bottom.
Okay, then you have to think a little bit, because you know, if you define it in this way, it's almost by definition like that. It's sort of the definition. Yeah, so I don't write it all, but it's not difficult. You know, it's just.
The definition is to minimize the norm of x b, and the equality is across straight.
Yeah, subject to. Yeah, subject to. Very good question. Thanks. That's the idea. Okay, so we start again. So here's the linear model again. Unknown regression functions, and I'm going to look at lower bounds and upper bounds, but mainly I want to show something new, so lower bounds, and let's just for lower bounds to assume noise, Gaussian noise with unit variance is maybe a good starting point. P parameters and observations, and it's high dimensional. So here's the lasso. Yeah, that's I guess most of you are familiar with it. And also the motivation, so I'm not giving that. If you want to ask me, but It's good motivation to do it this way if you think of sparsity. And the tuning parameter, that's something to remember. It's usually of order square root log p over n. Okay, that will occur from time to time. So this is the active set. I've written that on the board. The size of the active set is the sparsity, which is assumed to be small, whatever that means. Okay, and like I said on Friday, so typically, if you look at the prediction error, that's this. Typically, it behaves like the number of parameters divided by the number of observations, but the number of active parameters times a price to pay for not knowing the active set. Okay? So typically, it behaves like this. So if I take log p divided by n, that's more or less the tuning parameter squared, so it's S0 times lambda squared. So you see it appear here, S0 times lambda squared, but there's a constant in the bottom there due to, you have some kind of identifiability conditions. Okay, so actually, so I want to show that this compatibility constant, which actually appears there, is really needed. So I want to establish tight bounds for the lasso, for the prediction error, for a start. And you can ask why. Well, the main reason to look at tight bounds is to show that these kind of compatibility constants are really necessary. Well, on Thursday I'll talk a little about the de-biased lasso, and there you will have the situation where you do a lasso when actually the true parameter is not sparse, and then you maybe want to know what happens. And this is largely still an open problem, but I'll talk about on Thursday. And it's nice mathematics, I think. It has some geometry. I'll talk about the geometry of the problem. Okay, now I'll just put down the main result, and there are some conditions which are of the form the true underlying parameter. If it's not 0, then it's not going to be below the noise level. And that's called beta-min condition. So a beta-min condition is of the form like this. So the noise level is more or less square root log p over n. If you go below this level, you cannot really tell whether the parameter is 0 or whether it's small but non-zero. So if you're away from that, that's like this. So there's a constant here, so it's of larger order than square root log p over n. And I'll need such conditions. Now, as a statistician, you don't want to assume that if something is non-zero, then it's large enough so that you will notice it. That's what this is actually assuming. So this is a very bad condition from a statistical point of view. So usually I don't assume it, but for lower bounds, it's, I think, okay. Huh? So for computer science, they are okay also as well. They always assume this because they say, if you don't assume it, then I can't find the active set. But for statisticians, I mean, we can discuss this, but if you're honest, you don't assume that for inference, but for lower bounds, I think it's okay. So in contrast to upper bounds, because this is just a condition to make life easy. Okay. Then I come to this compatibility constant. So I'm now that's why I put a hat there. I'm going to look at random design, and I take the expectation of the Gram matrix. So that's now a deterministic P times P matrix. And I'm going to consider that quantity, which I wrote on the board, but now replacing the Gram matrix by its expectation. So if you have random design, this would be a random quantity, but now I just have a deterministic quantity, and I call that the compatibility constant. So that's a very funny thing. You have a quadratic function here, which you want to minimize, subject to a constraint, and this is a non-convex constraint. Yeah, so you end up with a non-convex optimization problem. Actually, what I'll just tell you now is, I'll give you an example later on, I hope I have time, where I can explicitly calculate that thing, but in general it's not so easy. Okay, so this is the beta-min condition that I'm going to assume. So it's on the slide, but don't worry about it like this. I mean, maybe you like to look at it, but just that I've shown you it, but there's some condition there, and then comes the following result. Okay, so you have this, say your design is random, and say it's the columns or the rows are IID copies of some vector with some covariance matrix sigma 0, think of it like that. And to normalize it, I just assume, say the diagonal of this matrix is all ones or at least bounded by something. I mean, I'm just have to somehow normalize. So let's say all entries are bounded by 1. And then this is important. This is not a normalization. I'm going to assume that this largest eigenvalue then is not going to grow too fast. So this maximal eigenvalue condition is also occurring very much in the literature. So now comes the result. This is a tight bound. So assume this beta-min condition, Gaussian design with a covariance matrix with the largest eigenvalue of small order log p. So typically people assume it's bounded, but it's allowed to grow a little bit. The usual value of the tuning parameter, the usual assumption on the sparsity, and that's usual because, you know, if you look at this, you want it to go to 0, right? So lambda squared, that's log squared, log p over n times s0, you want it to go to 0. So that's what I'm assuming here. You want some kind of convergence. Okay, so that's this condition. And there's some little technical conditions here. Some convergence, so also if S0 is a little bit larger. Okay, and then the prediction error of the Lasso has this bound. You see it's just exactly like here. Now an equality here. Of course not exactly. It's asymptotic theory. So with a small order term coming there. Yeah? So this says you can't get away from this compatibility constant. It just gives you exactly the tight bounds.
But this is compatibility not for design matrix, but for its expectation.
Yep. So I'll talk about that one too, but it's more complicated there. Mm-hmm. Yes. Yes. So I have to explain a few things. The beta-min conditions. Maybe I'll not go too much into all the technicalities. So let's first just explain this compatibility a little bit further. So this is my notation. I have written it on the board. I do it again. If you have an arbitrary subset, just put everything outside the subset to 0 in this vector and leave the rest untouched. And that's called BS. You can do that for an arbitrary vector. And B minus S is the complement operation. Yeah? Okay, now we're going to do some linear algebra. If you have a matrix, a symmetric positive semi-definite matrix, you can define its minimal eigenvalue. And if the minimal eigenvalue is positive, you can identify the vector B from this quadratic form. Okay, so it's like positive minimal eigenvalue gives you some identifiability. Now we're in a situation where you have an active set and a non-active set, and then you can define, if you have two subspaces of linear combinations of the columns of linear combinations of variables in S and variables not in S, you can look at its canonical correlation.
This is still coordinating form, right? B is missing here, yeah?
Oh, sorry, yeah. Here's a B missing, thanks. Yes. Here's a B, so just canonical correlation is defined like this. Well, canonical correlation, so it's the angle, and if you have an angle between two vectors, you can also look at their distance, and the distance is then 1 minus that angle if they're normalized to be equal to length 1.
Actually, it's probably inner product, right? It's
yeah.
Inner product between B, so it's not, yeah, it's
yeah. Maybe I did the normalization wrong. That could be, but I'm just writing that for two vectors, x and x2, if they have length 1, it's 2 minus their inner product, right? If they have length 1. So that's, I'm thinking in that direction.
Not 1/2 of the difference, right?
Yeah.
Of the difference.
Maybe the 1/2 should be here. Yeah.
But sigma dot 1/2 is applied to the difference of two vectors, right?
Yeah.
BS minus
Yeah, the difference of those two vectors. So B, yeah, let's see. B is BS plus B minus S, right? Well, or minus, whatever. Yeah. So, now we go to the L1 world. And you can try to write down similar things in the L1 world. So you just look at the minimal eigenvalue. I should have changed the notation here. But you just look at the minimal eigenvalue. But instead of the restriction that the L2 norm is equal to 1, you restrict the L1 norm to be equal to 1. Maybe the 1/2 is on the wrong place again. You can also look at some kind of L1 canonical correlation. So again, I forgot the B here, but I replaced the L2 norm here by the L1 norm. Yeah. And then there is this normalization with S. That's because if you go from L2 norm to L1 norm, you say, okay, if you have active set with size S, then the L1 norm is square root S, is bounded by square root S times the L2 norm. So it makes sense to normalize with the size, because the L1 norm of something is typically much larger than the L2 norm. So you need some normalization if you want to compare. So the compatibility constant, if you look at the the one you find in the literature, compatibility constant, it's something like canonical correlation. You replace the L2 norm by the L1 norm, and here's an inequality sign. And here's not 1, but maybe some other constant. But it's something like L1 type of canonical correlation. You just compare linear combinations in one space with linear combination in the other space. And then you look how far are they from each other. And this is the new one, which I've written here, which gets even more complicated. So it's like here, except that you, instead of this restriction, you have this restriction. Okay, and it turns out that's the real thing that plays a role in the lower bounds. So it's a little bit, if you look at this, it's a little bit, so if you put here, I think one of them, if you put somewhere, if you change a little bit the definition, you get the restricted eigenvalue, but you might also know.
So U is smaller than 1?
U is smaller than 1, yes. Typically it's smaller than 1.
So you give less weight.
Yeah.
Beta.
Very good, yeah. So you want it to be close to 1 because then you subtract more and then that helps. It makes you want it to be large because you're dividing by it. And if this is large, if this is 1, you're happy. This is what I'm doing here. But you have to make it a little bit smaller than 1 if you have to deal with noise. But depending on the situation though, yeah. Okay. So this is the old compatibility. I can give a geometric interpretation there that you just, let's see, you have here this restriction. Make sure that the first part is you take the convex hull well, signed convex hull of the variables in S. And you look at the signed convex hull of the variables not in S, maybe you blow it up a little bit, and you look how far they are from each other. That's what this is. And then you get this picture. So this is just, the active set is just one variable, and all the other variables you take the signed convex hull, and then you look at this distance, and that's the old compatibility constant. But now it's this new one is a bit more complicated, has a more difficult interpretation. Okay. So the new one is bigger than the old one because, well, so that means it's you may have gained something because you're dividing by it. Increasing in U, that's true. You want U to be increasing in U. Yeah, let's see. Yeah. You want U to be large. Yeah. And if you can take it equal to 1, you're happier. So here we take it, here there's no U here. There we take it equal to 1. So that's, now we understand compatibility. So this is, we know that the upper bound depends on the compatibility constant. We can prove that under the conditions of that theorem which I started with, you have this upper bound, and for that you do not need any beta min conditions. So you don't need that the non-zeros stay away from 0. This is actually a new result, and this is the result in literature, which is a little bit, you know, here you have nice remainder terms which are nice, and here is just order of magnitude, and there's this U and so on. So it's a little bit cleaning up the situation from the literature. Okay. Let's see. I think I'll just skip this part, except this part. So if you look at this non-convex optimization problem, what is important is to show that the solution will have non-zeros inside the set S. And let me just give you the geometry of that. It's kind of nice, I think. It's quite trivial, but so here's the L1 ball. Okay, here's 0. And maybe you know this picture that, let me try to draw it. This is the picture in the book of Cheap Shirani, Hasty, and so on. So here, if beta 0 is here, and you want to minimize the L2 distance subject to the L1 norm being equal to 1, then you hit a point and you get a sparse solution, right? That's the idea of the lasso. But we're in a different situation. Here's the L1 ball again. And now I want, well, forget about this minus S part, just put it to 0 for a moment. Then I want to minimize the ball subject to the L1 norm being equal to 1. So what I'm actually doing is, let me see. I forgot how it goes, but the idea is you're sort of trying to blow up a balloon here, right? And if you do put the balloon in a box, it will never go in the corners, right? No matter how hard you try. I mean, not my balloons. So it will not be sparse. It will not be a sparse solution. Yes, it's more or less like you do a balloon outside until it's inside the L1 ball, and then it will not be in the corners. And you have to do a little bit of arguments here because it's in high dimensions, you never know, but it turns out to be like that. Yes, so you get a non-zero solution, which is kind of good for the theory. Now let me skip all this. Okay. I don't know about time. Let's see. I'm assuming this quantity is going to 0, and that's a little bit more than assuming that you have convergence in the first place. I assume convergence for a little bit larger sets as well. Okay, let's see. And then for the noiseless lasso, that's like there, but now for the Gram matrix replaced by its expectation, you get the following results. So I'm comparing now the noisy lasso with the noiseless lasso. Take your tuning parameter of order square root log p over n. Here's a quantity which is going to 0. That's why I put it in green. And then with large probability, the prediction error of the lasso, if you compare it with the prediction error of the noiseless lasso, it's the remainder, the difference is of smaller order. So this result says, you might as well look at the noiseless lasso because the bias dominates the variance. And you can think of this as the bias. And so, yeah, what remains is of smaller order. Okay. Yeah, so this difference is of smaller order than the quantities itself. Okay, so you just can't forget about it. It's smaller order. Yeah, so this is like the noiseless lasso, the prediction error of the noiseless lasso is like the bias. And if you then compare the noisy lasso with the noiseless lasso, that's like the variance. And that theorem which I just showed you says that this term is of larger order than this term. Okay, so you might as well look at the noiseless lasso to get tight bounds because that's the main term. Okay? Yeah, so asymptotically these two are equivalent. This is a little bit about the kind of theory you use to prove this kind of result. Nothing very new. And then, once you know that you only have to study the noiseless lasso, the prediction error of the noiseless lasso, you can find an exact result under, but then you need these beta min conditions. Okay? So that's where you get the tight bounds from. So far, okay. Let me check with time. Yeah. Oh, there. Thanks. So to prove this last term, you need some results from non-convex optimization. And you need this. I really need very much that the solution will have non-zeros here, that you can't blow up a balloon in a box and get to the edges, to the corners. If you combine the two theorems, you get the lower bound for the noisy lasso. Okay. So this is all about random design. And now let's go to fixed design. So we considered Gaussian design. What about fixed design? Again, let's start with the noiseless case. So the noiseless lasso is the one which was on the board now, but now with here really the Gram matrix and not its expectation. So so this is now a fixed matrix, so it's everything deterministic here. And then you have to change nothing. You can apply the previous theorem. It's just nothing changes. It's just a different notation. So you can get the same result, but now the definition is with this matrix. It's just a different matrix there. Okay. So for the noiseless case, we are done. So let's consider an example. And the example is for the total variation penalty. So let's consider a function. Well, let's say a function evaluated at n points. So then it's a vector, an n-dimensional vector. And then the total variation is just the sum of the absolute value of the difference of each jump. So how large is this, how large is this, how large, and so on. That's total variation for a function only evaluated at endpoints. And do the lasso with total variation penalty, still noiseless. So I minimize. I have a fixed function, which I don't know maybe. Oh well, it's a bit artificial. It's a noiseless situation. I want to recover this function. I do the residual sum of squares. Well, the sum of squares, so the L2 distance, and a total variation penalty. So that's like a noiseless lasso. So you can always write a function defined on those endpoints as x times b. So that's kind of obvious. But let me try to put it here. So a function f I think it's like this, k equals 1 to I. If you say f0 is 0. Okay? So these are my vectors, my b. This is my b. So and then I sum from 1 to 1, so I can write a sum bk indicator k less than I. Yeah? So that's my X matrix. Okay, so you get this X matrix, this design makes those B's. So you have a lasso problem. So it fits in the framework that we considered so far. Okay, then there's a little bit a myth or a gossip going on that if you do the lasso, it won't work if the columns of your designs is highly correlated. Now let's look at this design. Terrible high correlations between the columns, right? Correlation meaning inner products. If you take the inner product of those two, divide by n, it's almost 1. So the huge correlations or inner products. This example still shows that the lasso still works. I'm going to calculate the compatibility constant. So we have a function and say it's just piecewise constant. Well, it's just defined on a few points. So it's like this, maybe like this, and then like this. And then let's see. This is the point where the first jump is occurring, and here is the second jump, and so on. Yeah? So the distance between jumps are the d's, dj. Then the compatibility constant is equal to this. So there's an exact expression for that quantity here, which depends on the distance between jumps. Okay, so this is an example where you can really calculate that thing. Okay, and these are the so it's a minimizer over some b's, and the b's, the exact where the minimum is attained, are those b's. Well, it's the inverse. You see the inverses of the jumps appearing. The inverse of the distance between jumps. Now, if you have this beta min condition, and the beta min condition now says that the jumps have to have a certain size. They have to have a certain size. Okay, so if the distance between jumps is like at the same order as n, the size is more or less the noise level, but otherwise it has to be larger. Okay, and then you get this, for this particular case, you get, it's the tight bound, so it's lambda squared times the compatibility, S0 divided by the compatibility constant, so it's like this. And if you look how it scales, so if the distance between jumps is the same all the time. And if there are S0, S0 plus 1, so you calculate the first value where the function starts is a free parameter, so let's put that's an active parameter. So you have S0 jumps plus where it starts, so it's S0 plus 1 free parameters in a sense. So that's S0 plus 1. If equal jumps, then the maximal 1 over the jumps, the maximal value is then S0 plus 1 divided by n, and you do the calculations, and you see that the prediction error is of order the number of jumps squared times log n over n, where log n over n is just lambda squared here. But anyway, if you have only 1 or 2 jumps, you get a parametric rate. Okay? The parametric rate in the sense of 1 over n and then the log term, of course, because you don't know where the jumps are. And you can extend this to trees. If you have a total variation penalty on trees, you just, for instance, just cut up the trees into path graphs, and you do it for each path, and you get similar result. Okay, so you can do that for more general graphs. Okay, now just to finish up a little bit quickly, you can do the noisy case like before. But it gets a bit technical, I must say that. So it's maybe good not to go into all the technical details. But you get something like, because of the noise, you get in the compatibility constant some weights. So they're here. And let's see. Just to say how it goes. It's result of papers of Arnak Dalalian and Mohammed Heberi and Johannes Lederer. Very clever. It says, okay, all you have to do is kill you somehow. Why do you use a penalty in the noisy case? That's because there's noise. And somehow this penalty has to get rid of the noise. Somehow kill the noise. And the amount of noise it has to kill is less if you have higher correlations. Because what you do, you have your active variables, your non-active variables, and then you just project those non-active variables on the active ones, and what's left over, that's the part of the noise that you have to kill. The inner product of that part with the noise. So if there's much correlation, and you project and then see what's left over, then there's hardly anything left over, so there's hardly any noise to kill. So here's this all defined. This is the projection. Well, this is just the usual thing. If you do these squares and you know, oh no, this is the projection of the non-active variables on the active variables. And this is what is left over. And this is then the covariance matrix of what is left over. And then you look at the diagonal elements of this matrix. And more or less what you have to kill the noise, you need your tuning parameter to be larger so that you put this quantity without the square in the weights here. Okay, so if there is more correlation, this will be very small, and then you put 1 minus that quantity in the weight, so it will be almost 1. Okay, it should be somewhere. So what I'm saying is, you only need that part of to kill that part of the noise that is left over after projecting on the active set. So if you have high correlations, not much to kill. Okay, and then the weights stay close to unity, and then you can almost take constant 1 here. So let me just give the result. So the upper bound is from this paper. Well, it's also in other papers, but I think the real result is in this one, Dalalian, Heberi, and Lederer. So it's very nice. You see the compatibility constant, they actually have it. And instead of a 1, you have 1 minus something small here, depending on those projections. So you see again, lambda square root S0 defined by compatibility constant like we had there. But now for the noisy case. And the lower bound is similar, a little bit. I'll skip all the definitions. The lower bound is like this. These are smaller order terms, lambda times sparsity and then the compatibility constant, and with instead of a minus you have a plus now. And then you just have to hope that the two are close to each other. That depends on the design. Okay? Just to finish, if you apply that to the total variation penalty in the noisy case, so now it gets really interesting because that's what we do. We have a noisy observation of a function with bounded variation. We do the total variation penalty. We calculate those weights. This is really hard work, I must say, but it's done in the paper by Dalalian and all. And then you get the following result. So the upper bound was known. And for the lower bound, you apply the previous result. And for this special case, you get this. So you get the lower bound and the upper bound, they differ only in this term. So you get really quite tight bounds for the total variation penalty. And so it depends. Well, this is in general not the dominating term. So what you will see, so if you have only finitely many jumps, say 3, then this will be the dominating term. So you get a parametric rate, that's lambda is parametric rate, 1 over square root of n. Let me put it down again. Log p over n in order. Here. So this is the 1 over square root of n, that's the parametric rate. Then there's a log p term, which is p is now n. So there's a log n term, and then there's an additional log term. So you get the parametric rate up to a log term, not a square root log term, but a log term. Yeah, and if the number of jumps is growing, then this will probably not. It depends on how large. But then this can be the dominating term. Yeah. And I don't know whether this is the tightest possible result, but at least it's up to log terms. You now see how tight it is. Yeah? Of course, you can. This can also be extended to more general graphs. This is work with Francesco Ortelli that I've just. It's on arXiv. So let me give a summary. So for random designs, you need these eigenvalue conditions. But then the bias dominates the variance. And for the bias, you have exact expressions for the prediction error under these beta-min conditions. And for fixed designs, there are upper and lower bounds, but then there may be a gap because of the constant here. And you know, it's not a priori clear how big the gap is, depends really on the design. Okay, now let me, this is all nonsense, so you don't need to look at it. So I have to, these acknowledgement people I talk to from convex optimization and non-convex optimization to help me out. Thank you very much for your attention.
Any questions?
Do we have analogous results for the fixed design and random design when we have heavy tail noise, like to get sharp bounds, similarly sharp bounds?
I don't think so. Heavy tilt, you mean infinite variance or?
No, I mean bounded variance for
Okay.
second moment.
Let me think. You get similar bounds, but not with exponential probabilities. I guess that would be my guess. Depends on if the design is bounded, at least. So bounded axis. Yeah, then I could do similar things, but then the probability is just not going exponentially fast to zero.
It's
Yeah.
going to be inverse polynomial because you will use concentration inequalities for stable noise, for example. And this will exist, and they will lead to not exponential,
Yeah.
but inverse polynomial.
Exactly.
Depends on the heaviness.
Mm-hmm.
But I think the best thing, or just for this type of estimate, really achieve the
This
rate.
you don't know.
No, it's okay. You need just you have your noise, which is a vector, and you have another vector which is fixed, and you just need some bound of high probability for quantities like this. And if there's second moments, you know there are many of them. So if there are second moments, you can use some kind of, what is it called again? I forgot how it's called, but you have uniform bounds also if you only have second moments. Yeah. So it should work. I think.
More questions? We're a bit out of time already, so if there are no questions, there will be one more lecture on thanks Sara again, and there will be one more lecture on Thursday at 3 o'clock. Okay. Thank you very much.